Okay, so without further ado, let's introduce Adrian Porch and his talk all about microwaves and marshmallows and electromagnets.
Yeah. We're a very traditional engineering department, but we do weird and wonderful things with microwaves as well. And it's quite good fun, you know, you let your imagination wild. What can you do with microwaves? So I thought I'd just go through some of the things that we do, and there's an entertaining little experiment as well halfway through. And you can eat the product, which is quite nice as well, so get to that in a bit. I haven't tried it on this microwave, so it may be a disaster, but I can tell you what should happen if it doesn't actually work. So microwaves, anyway. I know some of you are technical, somebody maybe from an art background, so there's a bit of a mix for everybody in here. 1 or 2 equations as well, nothing too deep. Microwaves are indeed waves, but they're of the electromagnetic variety, okay? So if you look at a microwave, this is what microwave means to me anyway. So electromagnetic wave, you've got a red bit there, which is the electric signal, and the blue bit, which is the magnetic signal, so locked together, okay? And if you sat there, it's a bit like a water wave really. If the red bit was a water wave, you'd bob up and down, wouldn't you, as it went through you? And that's basically what microwave does to us. It doesn't cause us to bob up and down, but the red bit causes heating, you know? But that flashes on and off, you know, billions of times a second. So frequency here, 1 gigahertz is 1 billion times per second, 100 gigahertz is 100 billion times per second. So these are pretty rapid, you know, variations we see. But the wavelength, which is how long it repeats in distance, you know, is typically 30 centimeters, you know, it's about this big, down to about 0.3 centimeters. So 30 centimeters corresponds to that frequency, and the 0.3 centimeters corresponds to that one. So it gives you an idea of what we're talking about here. Microwaves are all around us, you know, they're ubiquitous. Everyone has a mobile phone now. And 3G in the UK, you know, operates at about 2 gigahertz, so that's a wavelength of about 15 centimeters, you know, about the size of a small ruler, that sort of thing. But interestingly, if you look out into space, you know, if you've got a very sensitive lot of electronics, you know, geared up to an antenna, and you point it out into space, you see things like this. And that's the famous, you know, cosmic microwave background picture taken by the Kobe satellite. It's one of the most remarkable images in the whole of physics, actually. And this is the cold remnant of the start of the universe, basically, the origin of the universe. So what we're seeing there is something that was very hot, and has now got cold because the universe has just expanded. And the temperature of that is about 3 degrees off absolute zero. Like, we all emit infrared, you know, so we all heard of infrared cameras. So our skin is on, you know, it's about 300 degrees Kelvin, you know, to 20 degrees, 30 degrees C or something. Cool that down, instead of being infrared, you get longer wavelength, you get into the microwave region. And interestingly, I think some of us are old enough to remember analog television, yeah? We used to switch that off at 12 o'clock at night, you know, after the national anthem and things like that. And you see this fuzz, and of course you often wake up to this fuzz, you know, having come back from the pub or whatever. And about 1% of that is cosmic microwave background, which is quite interesting, isn't it? You know, if you detune your FM radio, about 1% of that is cosmic microwave background as well. So we're bathed in microwaves. The microwave background peaks at about 100 gigahertz, but you know, there's a sizable signal down at the sort of frequencies that we use mobile phones at as well. So microwaves all around us. The thing about microwaves, they are electromagnetic waves, so they're like bouncing off things. You know, you can see yourself in the mirror because, you know, the waves bounce off it. Metal surfaces are very good reflectors of microwaves. So we can use that, and we use it a lot in our research really, because you go back to that picture of a microwave as being a wave, and then of course if you have 2 metal sheets, for example, you can cause the wave to rattle around in it. And a lot of what we do is based on that principle, okay, as I'll try and explain in a bit. Now, you're all familiar with musical instruments, for example. What we got here is a bloke with a string, and it's being wiggled, he's just wiggling at one end. Unfortunately it's not a video, it's an old picture. But what's happening there is you've got waves bouncing around in 2 directions on the string. It's a bit like you know, microwaves bouncing between 2 metal plates. And that's called a standing wave. If you get the distance between the ends just right, you get this thing called constructive interference. And these, of course, are notes, aren't they? You're doubling the frequency there, tripling the frequency, quadrupling the frequency. And if you look at the vibration, you see the vibration is maximum in the middle there. In this point, you've got 2 maximum vibration positions. Here you've got 3, here you've got 4. You know, so the frequency, like that's 1, that's 2, that's 3, that's 4 in sort of simple units, okay? And if you look at these hot spots, which are where the vibration is maximum, they're called antinodes, then they're separated by half a wavelength. And you get that with microwaves, okay? You get that specifically in a microwave oven. So this is where I try the experiment that probably won't work, okay? In a microwave oven, what you'd expect actually are hot spots, because what you've got with microwaves, you see a maximum electric field disturbances at positions like that. And inside a microwave oven, what you've actually got, not 2 metal plates, but actually 3 pairs of metal plates that cause the microwaves to rattle around in there. So you get these hot spots forming. And although the front of a microwave looks like it's a sheet of glass, if you look at it very carefully, it's actually a metal grid. But it doesn't radiate because the holes are really small compared to the wavelength. So it acts like a metal grid. You can see inside of it. So what we got here is the classic discovery of microwave cookery, I suppose. A guy called Percy Spencer, who worked at the Raytheon Company in the mid-1940s, just after the war, 1946. So the folklore goes anyway, discovered that the bar of chocolate in his pocket melted when he stood next to a magnetron, which emitted microwaves. Now, he probably would have felt a bit of a warming feel, in his pocket before the chocolate melted anyway. Hence, microwave cookery was established. People discovered that microwaves heated things, and heated things very well. So it's quite nice to use chocolate. I did actually advertise this talk with MarshMallows, I think, and after minutes of ceaseless experimentation over the weekend, I discovered that MarshMallows just make an almighty mess, really, and it's quite dangerous because it's the hottest, stickiest substance known to man, I think. And I don't want to pass that around. So we got back to the traditional chocolate, I'm afraid, but you can try this at home. So what I've done is I've just put on an ultra low absorbing microwave composite, which is cardboard, and a bit of paper, and these are lucky stars. If you have young children, you know all about lucky stars, yeah? Lucky stars are quite nice actually, because they're like little aero chocolates, so there's not much in there. There's not much to heat up, you see, so they heat really rapidly, and because they're separated from each other as well, the heat tends to be localised. There's a lot of science in this, in terms of thermal design. I do have a secret ingredient that I was hoping to bring along today, but it doesn't quite work. But if it does work, I'll put a video on YouTube. You can all have a look at it on there, right? I'm not going to tell you what it is, but it's not chocolate. It's not marshmallows either. It's popcorn. Anyway, put that in there. And I think we probably only need about 20 seconds on this. Of course, it doesn't work then.
You haven't had a trial run with this microwave yet, have you? Oh yeah, you did before.
We're on. So what I've done is actually taken the turntable out, right? The whole point about the turntable is it moves the food through the hot spots. And if you move the food through the hot spots, then it all heats up uniformly, rather than overheating at different bits. So what's happening now, of course, is that we're actually heating it locally at different points. So it's, that's really what we don't try and do with the microwave. It can be quite dangerous, you can get things splashing up into your face. That should be more than enough, I hope, to have done something here. So I'll take it out, and this is where it all becomes rather arbitrary, you see. So what you then do is you take something like a key, which I haven't got. You didn't have a key on it. Yeah? Oh, yeah.
It's the real garage key.
So, you see, this is where I should have done it before, because that hasn't worked. We'll try it again. I'll just give it another blast. Give it another 30 seconds or so. I can see something happening in there.
It is cold in here. So
it's cold.
It's quite warm, so I'll give it another...
You have to press cancel.
Oh, cancel, yeah, what's that? Down there. Give it another 30 seconds. And so what will happen, I hope, anyway, is that the chocolate will melt at the hot spots. And the hot spots are half a wavelength apart, yeah? So if we measure the distance between the hot spots, and we double it, lo and behold, we get the wavelength of the microwaves. Okay? That's the idea anyway. I know the answer, so even if this doesn't work, we'll work it out anyway. And I can see them starting to melt now. And in any case, I'm going to pass them around anyway. They're much nicer when they're solid than when they're big mush. No. So, what have we got? Well, look at this now. We've got certainly some melting going on there. Yeah. There's a bit going on here as well. Okay. So we can keep doing this all the way around. So what we got there are basically two adjacent antinos. Okay. So I'm really sorry, Peter. You can lick it, you can lick it off. It's not going to work again. So take a ruler, and you can see from here that is about 6 centimeters, right? So I'll pass that around. You can eat the products anyway. They're quite nice. So some of them are a bit gooey.
Please eat them, you know, we don't want them back. So what we got then, 6 centimetres in between the anti-nodes.
Oh no.
So that gives a wavelength of, it's a bit messy.
I got an
so,
antinode.
It's only Johnny's got one so we're alright. So anyway, see, listen to Albert Einstein. The speed of light is a universal constant of the universe. Speed is equal to frequency times wavelength. So I said there was an equation in here. The wavelength is twice times 6, so it's 12 centimetres. But of course, to get the speed of light, you need to know the frequency of the microwave. It's a bit of a cheat, really. All microwave ovens have it stamped on them. So if you look inside the oven, in fact, it's just here on this one. Sometimes it's around the back. It says there 2,450 megahertz. Okay, great. So you assume that's right. So you put the frequency in. You've got to convert it into hertz. It's actually 2,450 million, you see, hertz. And if you multiply that number by 12 centimetres, which is 0.12 of a metre, you end up with, remarkably, 294 million metres per second. And of course, speed of light is actually 300 million metres per second. So, somewhat remarkably, it works, you see. So you can measure the speed of light with a microwave oven much more accurately than people could do 100 years ago, you know. So actually, the best known value we have at the moment is 299,792,458 metres per second. But I think Albie would have been happy with that, as he probably would have said, wow, you know. But things are not quite as simple as that. There's a bit of a trick in this, really, because what I chose there were 2 bits which I knew were 6 centimetres apart, and some of them are a bit further apart. And the serious stuff we do at Cardiff University are people like Panasonic, and believe it or not, Panasonic make microwave ovens in Cardiff. Do you know that? Up at Pen Twin, they actually make ovens. One of the few manufacturing things that goes on in Wales, I think, at the moment. And these are the sort of things that we do. We do computer simulations of electromagnetic fields within oven structures. And you see, things are not quite as simple as this, you know. It's actually a bit more complicated than that, because these ovens, you see, tend to get excited in lots of different notes, okay? It's just like the standing waves, you know, on a string, and you apply it into 3-dimensional space within an oven. But the other things that we get involved with, if you take the microwave oven apart, and I don't suggest you do this, because it's dangerous, really, for reasons which I'll explain in a minute. That thing there is called the magnetron, and the magnetron is the thing that's producing the microwaves. Those red and blue leads there, unfortunately, are about 4 kilovolts, so that's why you have to be a bit careful about this. But of course, for that to work, you have to have a mains supply. And what we're doing at Cardiff is we're taking a magnetron, which is that thing there, and you can see that the microwaves are actually emitted out of that bit, okay? This is the bit, unfortunately, where you have to apply very large voltage, because it's an electron gun device, the magnetron. It's been around for about 70 years now. But what we're trying to do is replace that with that. And this is a silicon device. It's a silicon power amplifier that Johnny there knows a lot more than I do about. And that's capable of delivering not quite as much power as the magnetron, but the interesting thing is you don't need mains. It works off sort of tens of volts, really, so it's easy, you know, easier, more portable. And 300 watts is going some, you know, in terms of the power. So we have a big effort in trying to sort of produce a lot more efficient, smaller, portable sources of microwave power. I'll pass this around because these are some of the bits and pieces that we make in our department. This is a project we've got currently with the School of Pharmacy. There's 2 bits here, actually. I'll pass them around together. This basically is the same frequency. This goes at 2.5 gigahertz. I'll pass it around. That's a custom-made microwave oven. And we put something in the middle of that and completely blast it with microwaves. Okay, so it's purpose-built, really. And this structure is also 2.5 gigahertz. And if you look at that, there's a little hole there if you hold it up to the light. And what we can do is, all the microwave power we pump into there, we can focus into that tiny little hole. So we can really blast things with microwaves. Now you may think, why are you doing that for, you know? Well, the reason is, well, one of the reasons is that we can take, in conjunction with the School of Pharmacy, for example, we are looking at bacteria like this. This is Clostridium difficile, which I'm sure you've all heard of. It's been a very nasty bacteria. These are hard nuts to crack, you know. They're basically spore-like bacteria. And to detect these, if somebody's ill with this, if somebody's infected with it, you need to find out whether they have it or not. And you can't get at the DNA. You know, these are spore-like bacteria. So what's been found is that you can target microwaves at these and crack them open, and then the DNA gets released. And actually the microwaves also assist the detection process. So actually we're developing ultra sort of microwave irradiation rigs like these to aid in the sort of diagnosis of harmful bacteria such as C. diff. The last thing I want to talk about actually, maybe overing a bit, I think we're 5 minutes late. Are we okay for time?
Oh yeah, fine.
Yeah, all right. There's other signs again here. Nobody's got a glass of thing, but if you have a glass and you ping it, have you got an empty glass there? Yeah, unfortunately. Do it forward as well. Ping, yeah. That's a resonance. You know, it's not electromagnetic, but it's acoustic. And of course, what's happening there? If you had a high-speed camera, then the glass would be doing this. You know, and you see these pictures, you know, on YouTube of glasses sort of doing this, and of course they shatter eventually. That's the ping. You know, if you were to measure the amplitude of the glass as a function of time, like on an oscilloscope, then that's the note. You see, it's one pure frequency. And if you fill that full of beer, which I'm sure, whose is this? Yours, is it? I'm sure you're going to fill it full of beer in a bit. But it doesn't ping, it clunks. Okay, if I hold it, clunk, you know, rather than ping. And what clunk does, that's ping. What clunk looks like is that. Okay, what's actually happening? It's still oscillating, but it's being damped. You know, so the blue one is when the glass is full. And we can do that in the microwave oven, you see, because if the microwave oven, for example, has nothing in it, it sort of pings, you know, the resonance is set up. There's nothing to absorb the energy. But if you put something inside it, like a foodstuff, then it tends to clunk. And if you looked at it in this way, this is what's happening with the blue one there, you see. You're absorbing the power. You're taking microwave power out of the red one, and consequently, the signal amplitude is falling off, you know. That's what the clunk looks like. But we tend not to do measurements like that. What we do is we look at the spectrum of the notes. This is called time domain, but we have a piece of equipment that allows us to look at the frequency domain. And what the ping looks like is that. It's a very pure spectral line. We say it's a high Q resonator. But if you put something inside that oven, so it absorbs microwaves, it clunks. And what the clunk looks like is that. Okay? So it's the same thing, only you notice we're plotting frequency on the bottom here. So what we actually do is that we actually measure the clunkiness of things, you know, in a microwave field. And it's called the damping factor. The two things we measure here, one of them is the shift downwards in frequency, and the other one is this broadening of the bandwidth, we say, the amount of clunkiness, the damping. And we can tell, we can do that with the material. We don't have to use a high power microwave for this, we can use low power microwaves. So we use the same process, but at much lower powers. And what we've done is we've developed this, we made this a bit of an art form. I've probably spent the last 25 years doing this, yeah. But this is work we got supported by the Wellcome Trust, trying to develop blood glucose monitors. Now I'm not sure if anybody has diabetes tonight, but it's a nasty disease. And one of the biggest problems, obviously, is the condition. It's actually, you know, managing the condition itself. You know, you can treat it, but management is key. But management is difficult because it involves drawing blood and it's very invasive, you know. So what we're trying to develop is a simple means where you don't have any blood extraction. Okay? So what we have is a circuit very similar to what I passed around. It's about the size of a £2 coin. It looks like that. Okay? Sticks on the skin, you interrogate it, and we look to see how well it clunks. And we can actually correlate that with blood glucose. No contact, it just sticks on like a plaster. Okay? And what we got here is the blood glucose that we measure compared to, you know, the standard ways of doing it. So the green one here is blood strip. So this is me over a 4-hour period or thereabouts, just taking on board 2 meals. Okay? And of course your blood glucose goes up. I'm not diabetic, fortunately, so I start off with a sort of normalish level, then I peak after I've eaten, and then it comes back down again, eat some more, peaks again. Yeah? What we got there is a blue signal, which is coming from our sensor, completely non-invasive. The green one is what's coming by taking blood out of your finger, and then the red one is called a continuous glucose meter, which is something that you actually inject into your side and sits in there as a sensor, then broadcasts a radio signal to a data logger that then tells you your glucose value. And that red one is the state of the art. You see, it's not very good, is it, really? You know, the blood strips work quite well, and our sensor works as well as the blood strips. So that's the stage we're at the moment, but what we hope to do is to actually produce a commercial medical device out of this. So the idea is that you buy these little little patches, you stick them on, you slap some electronics on the top, that's got the microelectronics, there's also a little transmitter in there, and then it chucks out the blood glucose value. So the idea is that this is called a non-invasive blood glucose meter. You can either send the data to a data logger, which is what currently happens, and it informs the person that their glucose is going up or down, you know, when an episode is coming on, so you're warned in advance. Or you could indeed send it to an insulin pump, which will then actually administer insulin. Got to be a bit careful with that, because you can kill somebody then, yeah? So that's maybe some way into the future, but what we want to try and do is have various others, so I may have missed people out there, but that's it. Thank you for listening.